This is Dr. Jackson. In this video, we'll be looking at horizontal and vertical strains and how they affect derivatives. So let's recall that a vertical strain by a factor of C replaces y by y divided by C, and it's going to result in a strain of the derivative by the same factor. Let's see, the proof here is because of the constant multiple rule. So if you're going to start with y equals f of x, and you strain it, you'll get y over c equals f of x, which is the same as y equals c times f of x. So now when you do dy over dx, it's c times f prime of x, which is a vertical strain of the original derivative. So to see this example here, let's start with y equals x squared, which is in blue here. Okay. And let's strain it by replacing y by y over 2, or equivalently g of x equals 2 times x squared. Y over 2 equals x squared. And so what is g prime of x? It is, it's 4x, which is 2 times 2x, or 2 times f prime of x. And so we get a strain there. So the strain here, the g of x, is twice as tall, stretched vertically away from the x-axis. That's the red one. And then the same thing is going to happen to the graphs of the derivatives. So the derivative of the original one, y equals x squared, is 2x. That's the purple line. And then y equals 4x, twice as tall, is the green graph, the graph of the derivative when we stretch it. So if you stretch it vertically, you're going to stretch the derivative as well by the same factor. Same thing as if you were to compress it. A horizontal strain by a factor C which is transformed. Let's see what happens there. So if you replace x by x over c, we're looking at y equals f of x over c. Now let's find dy over dx. Well, that's f prime of x over c. And then you take the derivative of x over c, which is 1 over c. So if you look at that, what we've done is we've taken the derivative, we've strained it by a horizontal strain by factor c, and then we've also strained the vertically by factor 1 over c. So what's going to happen is it's basically, let's say if c is bigger than 1, what we've done is we've expanded it horizontally and then compressed it vertically. So let's see if we can see this. Let f of x equal 2 to the x, and I'm just going to go from 0 to 3, and let's see, that's the blue one here. Starts at 1, 0 and ends at 2, 8, and it's curved up like this, concave up, increasing between there, that blue graph. Okay. Now, if we replace this, if we're going to replace x by x over 2, we're also doubling the x's here, so we're going from 0 to 6. And this is the stretched version, the red one. Notice the height is the same, but it's been stretched horizontally, twice as far from the x-axis. Okay, now let's look at the derivatives. Okay, what's the derivative here? If we take the derivative, let's see. Did I even work out the formula for it? Well, we can work out the formula. Okay. The derivative of the first one is natural log of 2 times 2 to the x. Okay, and the derivative here is natural log of 2 times 2 to the x over 2 times 1/2. Okay, so what's happened here is it's half as, let's see. First of all, it's twice as wide, but then it's also half as tall. So you take this point, let's take a point here, let's say the end point, it goes out twice as far and then halfway back down to here. Or a point here goes out twice as far and then halfway back down here. So it's twice as wide but also half as tall. Interesting.